Okay, so we're starting the second section of this track, and I'm glad to introduce Haya Sridharan, Technical Product Manager at Latent AI, and he's going to talk about expedited model deployment on edge with recipes. Thank you.
Test? Okay, cool. Hey everyone, thank you for joining. We're super proud to be part of the TinyML community at Latent AI, and the organizers have put up a great summit, and yeah, thank you all for attending. Really appreciate this. Today we're going to be talking about accelerated model deployment with Leap recipes. I'm Haya Sridharan. I'm a product manager at Latent AI. Before we jump in, I just wanted to give a quick overview of Latent AI. We develop software to optimize AI models. We're a team of 25 people, super passionate about AI and its applications, right? We spun out of SRI in 2018, and yeah, we're lucky to have a great set of investors, and yeah, super happy to be here. So I'm going to start with a small, edge ML story, right? Imagine that your company develops autonomous cars, and Solution Steve, who constantly interacts with customers, has figured out that one killer feature that's going to sell 1 million cars, right? He says, let's use our car's cameras and detect potholes. And data scientist Daisy, who loves hard statistical problems, remembers that she read a paper recently, and she's like, I think I can train a really great model that can detect potholes. And then ML engineer Evelyn says, yikes. The reality is, deploying production-grade models to the edge is incredibly hard. I don't have to tell this community that edge devices are resource constrained, right? You have to, ML engineers have to constantly make trade-offs between the model's accuracy versus inference speed, model size, memory, and then when you add power and cost, it becomes a really challenging optimization problem. But that's not all, right? This whole process is incredibly frustrating for developers. ML engineers, they have to tackle a lot of idiosyncrasies of various hardware targets. In fact, 2 devices from the same hardware family that are running the same models optimized using the same algorithms could produce 2 separate results. And this often results in extremely hardware-dependent workflows. Now, coupled with that, ML engineers have to also manually, optimize for multiple knobs. You can be like, what type of quantization algorithms should I use to compress my models? What type of accelerator libraries do I use during the compilation process, right? And then at the end of it all, you have to deal with the ability to have good runtime support so that you can actually take this model and integrate it into your application. And it doesn't end there. We've talked, some speakers have talked about the difficulty to iterate, right? And part of the challenge is you need to have really good diagnostics when something goes wrong. And you have to be able to reproduce these models, right? Like if you cannot reproduce models from run to run, fully optimized models, then you don't really know what's going wrong. And then you have the changing data landscape when you actually release your model in production and you start seeing all the false positives and false negatives. Whew. Given this ecosystem, it is really fair for ML engineer Evelyn to ask, is there an easier way to do this? That is the challenge that we are trying to solve with Leap recipes. Some of you may be familiar with the Latent AI Efficient Inference Platform, or Leap for short. Leap is a unified SDK built for machine learning engineers to compress, compile, and deploy AI models. And it works across any hardware target, framework, and OS. The Leap SDK is designed to provide fine-grained controls to developers across the ML lifecycle. For example, when compressing models, we provide multiple quantization algorithms like symmetric versus asymmetric quantization, powers of 2, etc. You can also apply additional techniques like tensor splitting and bias correction. And we're also constantly adding new methodologies like structured pruning. Now, Leap Compile involves taking a computational graph like a quantized model as an input and applying compiler optimization techniques like graph partitioning and operator fusion. You can compile across x86, NVIDIA, and ARM, as well as most architectures that are supported by LLVM. And the output is a binary representation called a latent runtime object. And our latent runtime engine, which is available with Python or C++, makes it easy to integrate this runtime, this latent runtime object into your application. We also provide ways to run, test, and validate the runtime with APIs. But we have to ask a slightly different question here, which is, if you are starting with an object detection problem today, is the right starting point for you to go to a GitHub and just like download a model and go through this process every time? Or is there a better way to do that? And building on top of the Leap SDK, we built this idea of Leap recipes. Leap recipes are a set of pre-configured assets combined with a set of instructions to follow to get to an optimized EdgeML model. Each Leap recipe tackles a type of problem like object detection or classification and is configured for a specific model and hardware target. It basically comes with the set of optimization knobs pre-tuned. For example, when you target a YOLO v5 model on an AGX, the Leap recipe will automatically use a symmetric per-channel quantizer with an NHWC data layout. This will produce an optimized model with a C++ wrapper, and it makes it easy for you to integrate it into your AGX. Now, we understand that good ML engineers, like many people here today, will probably be able to figure this out yourself, given enough time and resources. But that's going to be a manual and error-prone process. What we want to be able to do with Leap recipes is abstract the complexity away and help you focus on just your business outcomes. So let's take an example, right, of a recipe that we built. So we took the wildly popular, YOLO v5 large model, trained it on a COCO dataset, and optimized it for the AGX. As you can see here, it was 310% faster than the baseline PyTorch model, and also provided an 84% reduction in size of the model with less than a 3% drop in accuracy. So now, if you have a YOLO v5 problem, right, if you know you want to do object detection and you think YOLO v5 is your answer, what you can do is bring your own data and start with this model instead of going to GitHub. And as a side note, this YOLO v5 model, right, the large model, once it's been optimized, actually performs better than a YOLO v5 medium model that you would have gotten out of the box. So for some use cases, this could actually be quite significant. So what do Leap recipes look like? Leap recipes are a set of configurable YAML files. They can refer to each other in a hierarchical fashion. And they're built basically on software fundamentals like modularity and composability. Right? So the idea is that you can work on your individual components, right? You can use our zoo, or you could use your own models, your own data, and keep improving them. And you can also build them like a sequence of Lego blocks. So you can put them together and essentially compose a larger system. The nice thing about this type of a configuration-based approach is also that it is reproducible, right, and repeatable across different developer ecosystems. So just to sort of recap Leap recipes, like we help you create highly optimized models for the edge with great runtime support to integrate into your applications, and essentially help you create robust, repeatable, and reproducible models. Given these advantages, we believe that Leap recipes can give you a 10x improvement in your time to market, which is often a metric that we think about at Gleaton. And just as a side note, we're happy when ML engineer Evelyn goes from yikes to yippee. So looking at the bigger picture, Leap recipes can help you scale as an organization. And we are constantly working on adding new recipes, including a lot of recipes that we wish to target for microcontrollers. What we would love from you, like if you can come find us later, is like for the TinyML community to tell us, right? Like how can we add value to the community? Like where would it be helpful? Like what kind of hardware targets should we target, what type of models should we target, as well as candid feedback in terms of whether you think this type of an approach is beneficial. And yeah, in the interest of time as well, right? I just wanted to spend a little bit of time on these next steps. There's been a theme around, hey, how can we find the end users? How can we find, value to customers, et cetera? And these are three of the most common patterns that we've observed with some of our clients, right? And, places where we think we can add value. And I think this is useful for the community. The first is when someone wants to reduce their bill of materials. If you have like a hardware and, you don't want to spend as much money for it. Another is when you want to fit multiple models into sort of a single hardware. And lastly, like I said, if you want to accelerate your time to market, if you have these problems, we'd love to help. So please contact us at info@latentai.com. Thank you.
Thank you very much, Hayat. Very interesting talk. Thank you. Are there any questions from the audience? If there are no questions, there is a question over there. I'll bring you the mic.
Hello, thank you so much for this great talk. My question, assume that we have a large number of recipes. Have you thought about maybe building some semantic search or something to help me know which recipe is right for me, given maybe my task, description, model, specification, or target hardware, or even some SLAs that I have at the end user's level? I think that's going to be very important to be able to search or do the matchmaking between what the end users want, the target hardware, and the recipes that you have.
Absolutely. I think that's an excellent question. And we are working on an idea of a sweep. It is part of our roadmap, and we are actively working on it. And one of the key advantages that we see is this is not just going to be like a typical search, right? It's also going to actually involve running an inference on the runtime because it's part of our APIs. So every time we develop a new architecture, we'll run one inference. We'll see how it actually performs. But yeah, feel free to connect with us, and I'd love to talk to you more about this whole leap sweep idea that we're working on.
Thank you.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Syntiant. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving TinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SensiML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, GreenWave Technologies, Grovity, Hymix, HOTG, Imagimob, Itemis, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texil, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.